We have as our guest speaker Ken Larson, KJ6RZ, and Ken is an expert on how sunspots and the solar cycle affect the layers of the Earth's ionosphere and how that in turn affects the long-distance HF radio communication.
We all know that HF communications goes through the ionosphere. The purpose of this presentation is to talk about the activities on the sun that create the ionosphere and also disrupt it. So once we know what's happening on the sun, we can more effectively use the ionosphere by combining solar data with our understanding of critical frequency, maximum usable angle, absorption, and all of that stuff. But those things are a topic for later discussion. What we're focusing on today is what's happening on the sun that causes all this to occur. Early on, it was known that radio signal strength varied throughout the day and seasonally. By 1910, the maritime radio operators knew for certain that signals traveled better by night than day, were less noisy in the winter. The other thing that they firmly believed was that the quality of radio transmission was directly proportional to wavelength. So the longer the wavelength, the longer and more dependable the communications. And because of that, they operated from 50 up to about 1 megahertz. The marine distress frequency was on 500 kilohertz. Longer was better, so they would have operated at a lower frequency, but you can only get so much of an antenna on a ship before you run out of space. Amateur radio operators were exiled to 1.5 megahertz, thereabouts, 200 meters. And quite frankly, as far as the commercial and government radio operators were concerned, amateurs were a real pain in the neck. So they put us up someplace where we could stay out of trouble, they thought. And you can kind of imagine spending all your life on 160 meters. Well, that's what they did, because that's all they had. But the government helped us out in 1924. They gave us the bands of 40 or 80, 40, and 20 meters. And so, remembering that everyone, including amateurs, thought that longer was better, 80, 40, and 20, as far as they were concerned, was even more worthless than 200 meters. But a few brave people went up and tried 80 and 40 and 20 just to get rid of some of the crowding that was on our only band, which was 200 meters. Well, the movement turned into a stampede when it was discovered that on those bands you could easily work Europe and New Zealand, Japan, South America. So everyone was having a good time, but then the good times came to an end. By 1933, 20 meters had become completely dead, and no one knew why. It just died. In 1935, though, the shortwave bands came back to life, and it gradually became apparent that maybe performance on the shortwave bands was tracking the solar cycle. It was really a brave guess at that time. So what's a solar cycle? Solar cycle is nothing more than tracking the sunspots as they go from no sunspots at all to a large number of sunspots on the sun and back to no sunspots again. This graph shows the solar cycles from 1880 out to about 2010, I guess. And what you see in this is extreme variability in the solar cycles. The amplitude, which is the maximum number of sunspots at solar maximum, you see varies all over the place, from not so many to over 200 in 1957. The height varies, the width varies, the period varies. period is roughly 11 years, but can range anywhere from about 8 to 15. If we go back and look at solar cycle 16, in 1928 it peaked, and we had excellent communications on 40 and 20 meters. But by 1933, we're at solar minimum, 20 meters went dead, and then again 1935 it came back again. Well, this is all easy for us to see looking at this graph, why things deteriorated and came back. But the people at the time were working this real time. You know, it was the first time they had been on the shortwave radio bands. It was a real leap of faith to think that all this was somehow or other tied to the solar cycle. But they made a guess, and eventually it turned out to be the case. How do you count sunspots? Well, that sounds easy enough. You take, you take a telescope, you point it up to the sun, and you count them, right? But the problem is that today's telescopes are one heck of a lot more powerful than the ones they had back in the mid-1800s. So how do you use sunspot numbers as a measure of strength for solar cycles when you have technology changing underneath you? Well, they actually had this problem right at the get-go. In the early 1800s, they had problems from one observatory to another trying to settle on what the actual number of sunspots were. So Rudolf Wolf, working in the Zurich Observatory, came up with this equation where R is the relative sunspot number, G is the number of sunspot groups that people could count, S is the total number of individual spots, including those in a group, and K is the magic number. That's a variable scaling factor. And Wolf set K equal to 1 for his Zurich Observatory. Then all the other observatories were given various values of K that would relate their observations to what they were seeing in Zurich. Well, still use this formula today in coming up with the sunspot numbers that you see on the side of this graph. But of course today is a very, very small fraction because we have very good telescopes. So by adding the value of K to our observations, we are scaling it back to what would have been seen in Zurich in the early 1800s. Well, we rely heavily on the sunspot number for tracking the strength of solar cycles. It seems like with today's technology we could do a whole lot better than that. And we can. And one of the things we use is the solar flux index, which is a daily measurement of radio noise produced by the sun at a frequency of 2,800 megahertz, 2.8 gigahertz. And that turns out to be a very reliable method for measuring activity on the sun. During solar minimum, the solar flux index is around 65. During maximum, it can go up in the low 200s. I think today it's about 71. I checked before I came over. And what's interesting about all of this is you notice that our high-tech solar flux index is tracking very closely to the old standby sunspot number. So the two do correlate, and the old technology and the new technology turns out to be right in step. Skywave propagation. Appleton proved in 1925 that HF communications was actually going through the atmosphere. Before then, no one really knew how radio communications worked. There were all kinds of theories by very prestigious scientists and well-renowned universities, mostly in Europe and England. But through some very carefully contrived measurements, Appleton proved that the radio signals that he was receiving from a commercial radio station in London, I think, it was a very powerful station, was in fact coming out of the sky and not traveling along the ground. That was the first time that had been proven. There were theories that there was an electrified area up in the upper atmosphere and signal, and that was forming kind of like a transmission line with signals bouncing back between the electrified area and the ground. But no one could prove that that was the case until Appleton came around. Well, once I figured the radio waves really were going through the atmosphere, the next question was, why is it that the ionospheric propagation is so heavily dependent on the number of sunspots showing up, and then also why radio signals start bending immediately when they hit the ionosphere. The first question, why is the ionosphere so heavily affected by sunspots? Well, you can guess a good answer there. It's the sunspots that are generating the ionized region in the atmosphere. Good guess, but turned out it wasn't true at all. So the plot thickens. Looking at formation of the ionosphere is formed by intense, extreme ultraviolet and X-ray radiation from the sun. What does ionization mean? Well, it means that a neutral atom absorbs some of this radiation, which energizes its electrons. Occasionally, once in a while, an electron will gain enough energy that it splits off from the atom, leaving the atom a positive ion, meaning that it's lost one of its electrons. Occasionally is the operative word here, because there are 100 times more neutral atoms in the ionosphere than there are ions. So the ionosphere really is a very thin, wispy, easily blown around region. As this intense radiation hits the upper atmosphere, it's very intense, but there are very few atoms to ionize. So the ionization levels are very low. As the radiation penetrates further into the atmosphere, there are more atoms, the ionization levels go up. But ionization also weakens the EUV and X-ray radiation. So at some point, the radiation is far enough down into the atmosphere that you have a lot of atoms, you should have a lot of ionization, but the solar energy is simply running out of energy, and the ionization decreases. Eventually the radiation disappears, and that marks the lower edge of the ionosphere. We talk about the ionosphere, and that's what it is, but it turns out that the ions are way, way too massive to be affected by our puny radio waves as they go passing by. But the electrons aren't. They're very small, very lightweight, and they interact with our radio waves very readily. So for us in radio communications, it's electron density that's important, not ion density. We care less about the ions most of the time. Okay, skywave propagation. How does it work? The most important thing is that the highest level of ionization occurs somewhere around the middle of the ionosphere. Low ionization at the bottom, low ionization at the top, but a lot in the middle. So radio waves travel in a straight line from our antenna up to the ionosphere. As soon as it hits the ionosphere, it starts bending right away. But the question is, what direction does it bend in? It bends towards the Earth when it's passing through increasing levels of ionization. If it just kept bending, it would probably exit the ionosphere someplace in here. But that's not the case. As it starts going down back towards the Earth, going from high levels of ionization to low levels of electron density, it bends away from the Earth. So it straightens out, exits the ionosphere way out here, and then travels in a straight line to our antenna. So that's what's happening. Our radio waves aren't bouncing off or reflecting off of anything. They're bending as they go through the ionosphere and encounter either increasing or decreasing levels of electron density. So the trends of HF communications during solar maximum have a lot of radiation coming from the sun, corresponding to a lot of sunspots appearing up on the sun. Our ionosphere is heavily ionized, as well as the D layer. So during the day, 80 meters doesn't make it. It's absorbed quickly by the D layer. 40 may or may not make it. Probably doesn't during the middle of the day, but early in the day or in the afternoon it might be okay. But 20, 15, and 10 all are bent back by the ionosphere. Excellent DX conditions. During the night, the level of ionization decreases, of course, because there's no more sunlight to ionize the atmosphere, and you have a lot of recombination of electrons with ions. So 80 and 40 meters are bent back towards the Earth for nighttime communications. But take a look at 20 meters. For a while, it kind of makes its way back, but as you get further and further into the night, 20 meters goes through the highest density of the ionosphere, and now it's going from high density to low density, and when that happens, it bends which way? Away from the Earth, right? So it bends away from the Earth and lost to outer space. 10 and 15 meters, of course, are lost much quicker. During solar minimum, you have a whole lot less radiation coming in, few, if any, sunspots visible on the sun. So during the day, again, 80 meters is absorbed in the D layer, 40 meters comes through pretty well, 20 meters may or may not. It was working pretty good for you guys up on the hill not too long ago. But 10 and 15 is generally lost during solar minimum. At night, 80 meters comes on strong. 40 meters may hold in there for a while, but 20, 15, and 10 at night are all lost to outer space. Sunspots have been observed for a long time. This is a graph starting in 1600 when Galileo started looking at the sun with his telescope. What catches your eye real quickly is the Maunder Minimum, which we'll talk about in a couple minutes. But there's something else more subtle, and that are these periodic amplitude dips. Notice that these two solar cycles, the amplitude number of sunspots is much less than the ones cycles on either side of it. Another one here around 1900. Again, so this one's not quite as pronounced, but on either side of it, the solar cycles do get much more intense. And so what you notice about this is that these periodic dips happen about every 80 to 120 years. So there's one, there's two, is that number 3 happening on us right now? Well, it's very, very likely that that's going to be the case. And we'll talk more about that in a few minutes. Okay, the Maunder Minimum was 70 years from 1645 to 1715, when there were very few, if any, sunspots seen on the sun. Well, you know, you could guess that was a long time ago, and the scientists and astronomers really weren't that vigilant about observing the sun, but that's just not the case. A lot of very well-known astronomers and observatories were watching the sun all the time. There just weren't any sunspots. In fact, when a sunspot did show up, it was a pretty exciting time in the astronomical community. Wow, we got a sunspot. We haven't seen one of those in 5 years. And that's pretty much what the situation was. So, it turns out that the Maunder Minimum wasn't the only one. There have been other ones further back in history. How do we know this? We know it from radioactive carbon-14 in tree rings. Carbon-14 is produced by cosmic rays colliding with nitrogen in the Earth's upper atmosphere. Carbon-14 makes its way down the lower atmosphere, is absorbed during photosynthesis, and shows up in tree rings. The important thing is that during solar maximum, the sun's intensified magnetic field provides more shielding for the Earth, shielding it from cosmic rays, so we have less carbon-14 produced during solar maximum. During solar minimum, we get high levels of carbon-14. So by using the carbon-14 data, it's pretty easy to find out when these long periods of little or no solar activity occurred. So what's the implication of this? Well, for the last 300 years, sunspot cycles, solar cycles have been pretty regular, but this may not be the norm. It looks like these prolonged minimums occur at a fairly regular basis. One there, one there, one there, one. Are we about ready to get another prolonged minimum? Well, kind of looks like maybe we are, but I'm an old guy and I'm not going to last very long, so I kind of hope that we don't get a prolonged minimum anytime real soon. But sunspot cycles are weakening. It's interesting, from 1880 through 1928, the sunspot cycles were all pretty much the same, and then they peaked up after that, reaching a maximum in 1957, just before I got my novice license. And that's the highest that we have seen. Since 1980, they have been slowly decreasing in amplitude. Solar cycle 24, which we've just completed, was very similar to conditions back in the early days of amateur radio. So we're not worse off than the old days, but we're not any better either right at the moment. The projections at the moment is that upcoming solar cycle 25 will peak in 2025, and it's expected to have about the same amplitude as 24 that we've just been through. They're projecting a sunspot number of 115. Cycle 24, I think, was 118, 119, so the upcoming cycle and the previous one are going to be just about the same. The real bummer is this may be the last sunspot maximum I see, and it's not so great. You young guys can look forward to what's going to happen out here when we get back to the way it used to be with much more active solar conditions. It's also interesting, just looking at it, that sunspot maximum occurred in 1937, just before World War II began. So HF communications was excellent at that time. But all throughout the war, HF conditions declined. Sunspot minimum occurred in 1944 and persisted through the end of the war. But despite the fact that conditions were deteriorating all the way through the war, radio operators found a way to deal with that and get their traffic through, which they had to. That was the only form of long-distance communications. All the telephone lines, of course, have been cut. Telegraph lines were all gone. The only way you could talk to your ships at sea, of course, was HF communications. So the war was the early ages of radio communications. They were dealing with the solar cycle that they barely understood, and they had to make it work, and they did. So what are sunspots? Sunspots are black blemishes on the face of the sun. If you look at one up real close, the dark center, which is called the umbra, that's about the same diameter as the diameter of the Earth. So you could take the Earth and drop it into a sunspot, and that'd be the last you see of us. Sunspots vary a lot in their configurations. They all have an umbra, but they may or may not have a penumbra, or they may have only a partial penumbra. There's a lot of variation. Sunspots last from several days to sometimes a couple of weeks. Why are sunspots black? This is a pretty important deal. The hot plasma from inside the sun is carried to what we perceive as the surface of the sun via convection current. So the surface is heated by this convection currents. But when a magnetic field bursts through the surface, it prohibits this upward flow of the hot plasma. So the site where the sunspot is, which is where the magnetic field burst out and were plunged back into the surface, these two locations are cooler than the surrounding portions of the sun, and cooler means they look black. This characteristic is seen over and over for other phenomena on the sun as well. If a particular feature is cooler than the surroundings, it will look black compared to the rest of the sun. Sunspots rotate with the sun from left to right in this picture. If a sunspot is strong enough, when it disappears around the right edge of the sun, in about 13, 14 days, you'll see it come around the left edge of the sun. So why does the solar cycle occur? The answer is the very twisted, tortured, really messed up magnetic field of the sun. So the solar cycle thing is all about magnetic fields. If we look at the Earth's stable, well-behaved magnetic field, we get a better idea of the chaos that's actually occurring on the sun. So we'll take a quick look at that. The internal structure consists of the crust at the top, then the mantle, and then the outer core, which is hot, molten, liquid nickel iron. It's so hot that ionization occurs in the inner core, which means you have positive ions and electrons floating around in there. You would think the situation would proceed in the same direction as you get to the inner core, which is even hotter yet. You'd expect that to be just plain liquid. But instead, the Earth's gravity takes over and compresses the inner core into solid nickel iron. So the only molten part of the Earth is the outer core. And that's important because what happens is the hot plasma near the inner core is heated, becomes less dense, flows upward towards the mantle, cools, sinks back down again, gets heated, comes back up, so you get this rotating convection current of plasma. Well, plasma is charged particles. So in this circulation, you not only have plasma that's circulating, you've got electrical currents that are circulating. And according to Ampere's circulation law, whenever you have currents that are circulating, you have a magnetic field. In this case, it's the Earth's magnetic field that's created deep within the Earth. Turns out the Earth's magnetic field is quite important to us. I thought its only purpose was to point my compass in the right direction. But it turns out that the magnetic field produces a protective sheath around the Earth that diverts the sun's harsh solar winds. Mars lost its magnetic field. Mars was once similar to Earth. It had rivers, lakes, and even an ocean or two. And it also had a hot, molten inner core or outer core. But Mars is much smaller than Earth, and it cooled quickly. And when it cooled, its inner core or outer core, whichever, also cooled and solidified. And once it solidified, there were no more circulating plasma, no more circulating electrical currents, and Mars lost its magnetic field. And when that happened, the intense radiation from the sun ripped up Mars's atmosphere, evaporated its lakes and oceans, and left Mars the dead planet that it is today. The important criteria to take out of all of this is that if a planet's going to have a magnetic field, it must have a hot, convective, circulating electrical core someplace within the planet. And it turns out the same criteria applies to the sun as well. So if we look at the sun, the inner part is the core, which we'll talk about in a minute, and the radiation zone, the convection zone, and then what we perceive as the surface is the photosphere and an atmosphere, which is the chromosphere, and the corona being the very outermost part. The photosphere is what we see when we look at the sun, with protective eye shades or with a telescope with protective filters on it. That's what we perceive to be the surface, and it has a rather sharp edge, and so it looks to us like it really is a hard surface, even though in fact it's just gas, and its density is in fact less than that of Earth's atmosphere at sea level. The only way to naturally see the chromosphere and corona is during a solar eclipse. And in this eclipse, you can just barely see a red ring around what would be the outer part of the sun. That's the chromosphere, and then the corona is the white halo extending quite far out. And the reason it's white is the corona is actually dust particles out in what we would call space, because it's very thin atmosphere out there. In fact, the density in the corona is about the same density as Earth's atmosphere at the orbit of the space station. So it's pretty thin stuff. And what's happening is the intense sunlight from the photosphere is reflecting off those dust particles, giving it the white halo. We don't have to wait for solar eclipse to study the chromosphere. If we put hydrogen alpha filter on our telescope, we can see the chromosphere directly with all of its fine structure, which becomes important to us in a little bit. The sun's core, well, most of the sun, all of the sun, is composed almost entirely of hydrogen and helium gas, and trace amounts of all of the other elements in the periodic table. The third most abundant element is carbon, but it's only a few tenths of a percent. the huge size of the sun creates an enormous gravitational field which squeezes the hydrogen and helium into the core, where temperatures reach 15 million degrees, and the pressure is so high that nuclear fusion spontaneously occurs, which creates the enormous energy that the sun outputs. That energy output from the nuclear fusion just balances the force of gravity, which means that the sun stays in this balanced configuration for billions of years. Good news for us. The interior of the sun is radically different from that of the Earth. Instead of the core being surrounded by a convective plasma like the outer core in the Earth, on the sun, the core is surrounded by the radiation zone, which is a deep blanket of hydrogen and helium gas, 35,000 kilometers deep. The temperature gradients within the radiation zone are such that the plasma is, in essence, frozen in place. There are no convection currents, there are no circulating electrical fields in the radiation zone. Instead, the high-energy photons that are created by the nuclear fusion in the core pass through the radiation zone, but the radiation zone is so dense that these photons go hardly anywhere at all before they end up colliding with some other particles and are scattered. So they're scattered all over the place, have a very hard time getting through the radiation zone. In fact, it takes on the order of 170,000 years for a photon to make it through the radiation zone. Going through the convection zone happens very quickly, and it only takes 8 minutes for the photons to go from the sun to the Earth. So that means the sunlight that we enjoyed today started in the core of the sun about the time man first appeared on the planet, about 200,000 years ago. And that sunlight's been traveling all the way through the sun, through all of human history, and finally got here today. The convection zone is much different than the radiation zone. The convection zone is very similar to Earth's outer core. It's an area of plasma with convection currents, just like in the outer core of the Earth. So the plasma is rotating around and around, heated at the radiation zone, circulates up to the surface, cools, sinks back down, and round and it goes. It too is a plasma, so we have circulating electrical currents, which means we have a magnetic field. So the sun's magnetic field is then created in the outer portions of the sun near the surface, and that is part of the reason why we got such a messed up magnetic field on the sun. The other problem is that the sun's not a solid, it's a huge ball of rotating gas, and to make matters worse, the equator is rotating faster than the poles. The equator rotates in about 24 and a half of our days. The poles rotate in about 34 days. So this differential rotation is the other part of the problem that really messes up the sun's magnetic field. At solar minimum, the magnetic field is a nice dipole field, very similar to that of the Earth. The Earth's magnetic field is about 2/10 of a Gauss. That of the sun is about 1 Gauss. So the two fields during solar minimum are quite similar. But as we go from solar minimum for 3 to 6 years, as you can see, the differential rotation causes a nice bipolar field to get stretched and wrapped around and around the sun. As it does so, the field lines get twisted by the turbulence in the convection zone, so we have a tight magnetic rope which oftentimes knots and becomes even more intense. You can't keep winding this magnetic field around and around the sun forever. It's just not a sustainable condition. Something's got to break, and it does. The continued winding, twisting, and knotting creates tremendous stress in the sun's magnetic field, driving intensities to well over 3,000 Gauss. Eventually, the stress causes the field to rupture. And when it does, you get all the interesting kinds of things. This is a prominence. The prominence is actually an erupted magnetic field, leaving one sunspot and diving back into another. But it's carrying along with it the hot plasma from the sun, which is why we can see the magnetic loop in a nice, pretty prominence. While these are occurring, of course, the sunspots are occurring. They're at the base of these big magnetic loops. And we also have solar flares. A solar flare is this bright explosion, not the eruption off to the side. So, what happens is we start with a nice bipolar field. It gets dragged around the sun. It gets really knotted, it erupts, and then this field starts disintegrating and eventually goes back to a nice bipolar field. But look what happened in the meantime. The the magnetic poles flipped. What was a magnetic field north becomes the south magnetic field, and vice versa. Goes through another solar cycle, another 11 years. This happens all over again, and the poles flip again. So riding on top of our 11-year solar cycle, we actually have a 22-year cycle having to do with the poles flipping. Other than the solar cycle itself, the phenomena that most affect HF communications occur in the sun's atmosphere. We have prominences, which we just talked about a minute ago. This is a nice one against the black backdrop of outer space. When you see a prominence on the face of the sun instead of at the edge, it looks like these black wiggly lines. In fact, it is these black wiggly lines, which are called filaments. So filaments and prominences are the same thing. During the active period of the sun, you have sunspots, not only sunspots, but sunspot groups. The groups turn out to be very important. And you also have Plages, which are bright areas in the chromosphere, and solar flares. We're going to focus on the last two. So Plages are the bright, irregular shaped regions you can see in the picture of the chromosphere on the left. Plages form where there are intense radiomagnetic fields bursting out from the sun. And interestingly, Plages usually form near sunspots. Plages form before sunspots appear, and they disappear sometime after sunspots in the region have vanished. The very important thing is that Plages emit copious amounts of extreme ultraviolet light. So it is the Plages that are the source of the energy that energizes our upper atmosphere, creating the ionosphere. Sunspot connection. While there's a strong correlation between sunspots and long-distance HF communications, it turns out sunspots have nothing to do with HF communications at all. It's the intense EUV radiation from the Plages that accounts for the Earth's ionosphere. Sunspots are simply too low in temperature to generate the needed EUV radiation. However, You don't see any Plages up here in this view of the sun, in natural sunlight. The sunlight is just too bright for the Plages to show up. But sunspots show up very easily. So sunspots act as markers for Plages. If there are a large number of sunspots, that means there are a large number of Plages in the area. High EUV levels, strong ionization of the Earth's atmosphere, and good radio communications. So while sunspots don't create our ionosphere, they act as markers for what does. The energy output of the sun is also interesting. This EUV radiation that we depend so much on for radio communication turns out to be 1/1000th of 1% of the sun's total energy output. In fact, you can hardly even see it. The sun's energy output remains incredibly stable for thousands of years, but not so the EUV radiation. That's not stable at all. In fact, it varies over the 11-year cycle as Plages come and go. And so the Earth's ionosphere also varies over the same time period. We ought to take another closer look at the ionosphere. It's really nice that we got the ionosphere for our radio work, but it turns out that the EUV and X-ray radiation is incredibly deadly. And it's the Earth's ionosphere that shields us from this radiation, making life on Earth as we know it possible. So that's the really important version of, or reason for the ionosphere, is that allows us to walk around and come to this meeting tonight. The other part, that radio part, that's just a nice sidelight. Solar flares are sudden, massive explosions resulting from release of tremendous energy from strong magnetic fields. In fact, solar flares are the most powerful eruptions in the solar system. It's easy to figure out what a flare is. Just take the positive lead from your power supply and hold it right next to the negative lead of your power supply, let the two touch, and you get this big flash. Well, that's just exactly what the solar flare is. If we go back maybe a slide or two, we have these prominences, which are the magnetic field erupting and going deep into space, and they are coming out of sunspots at their base. Well, these sunspots, because of the differential rotation of the sun, they're moving relative to one another. So this isn't a nice stable prominence here. The foot points are moving with respect to one another. As a prominence goes further and further into space, it gets squished closer and closer together and twisted on top of that, and eventually you have a point where the magnetic field going up gets very close to the magnetic field coming down. You've got enormous energy between those two, and they effectively short circuit across, and that's what creates a solar flare. These solar flares, says the most powerful eruptions in the solar system. In fact, some of the bigger ones are so powerful that you actually have a nuclear reaction occurring way up in the corona as a result of the enormous pressure and heat generated by the solar flare. And because of that, you get all of this junk being radiated out from the flare. Gamma rays, which comes from nuclear reaction, X-rays, EUV radiation, visible light, even radio waves. In addition to that, you can have material ejected with the solar flare. So solar flare really throws a lot of stuff at us. The X-rays and EUV radiation reach us in about 8 minutes. The high energy particles get here in about 30 minutes. The shock waves and the slower corona mass ejections take on the order of 1 to 4 days. So when you have a solar flare and that flare is headed in our direction, we could expect 4 days of kind of disrupted operations. We detect the solar flare by rapid increase in the X-ray radiation coming from the sun, which is monitored continuously by the GOES satellites. I'll show you a picture of one of those in a few minutes. But this is a particularly interesting solar flare that happened in 2005. This is the picture of that flare taken by a Soviet spacecraft. And the way we measure the strength of a flare is by a logarithmic scale. Class A is the normal background X-ray radiation coming from the sun. B is a little higher background. C is a small minor flare, which probably won't have much effect at all on our radio communications. An M-class flare gets our attention because that can cause a brief radio blackout. The really bad news ones are the X-class flares, which can cause radio blackouts for quite some time. So each class is 10 times greater in strength than the one before it. So this scale is exactly the same as the Richter scale for earthquakes. A magnitude 6 earthquake is 10 times more powerful than a magnitude 5 quake. So that gives you some feeling for it. This happens to be the GOES 16 satellite that's up there now. Back in 2005, we're using the GOES 12 satellites. So the Earth's ionosphere reacts really bad to large-scale flares. This is looking at the D-level absorption of this very same flare. What is interesting about this flare is you read about what happens in the books, the ARRL books, and the sequence of events that happen, but you rarely get to experience one. Well, it just turned out that a couple of us were working in the radio room at the East Valley Sheriff Station in Thousand Oaks. We're participating in the California Emergency Services net. And what we did before each net, just to see how things were, is we'd check out how strong WWV and WWVH were, and we'd also check some other parameters as well. But before the net, those two stations were strong on 5, 10, 15, and also on 20 megahertz. 20 was a little bit weaker, but it was still there. The net went very well. Everybody heard us, we heard everybody else. The net closed, and so we went back to check WWV again, as we were supposed to, right about this point. And what we found out was 5 megahertz was gone. No signals on 5 megahertz. We turned up to 10. It was very erratic. It was bouncing in and out. But 15 and 20 megahertz were just fine, no problem at all. So then we went back down in frequency. 15, 10, and 5 megahertz were all gone. Went back up, checked 20 megahertz, and that was gone too. So that's kind of the sequence that you have during a flare. It starts wiping out the low frequencies and builds up to the higher ones. And now we know that what's in the literature actually is true, because we saw it happen. So if you look at this, it's kind of hard to see, but this is showing the absorption level by frequency. And you can notice that 5 megahertz is heavily absorbed by the enhanced D layer. 10 megahertz is pretty heavily absorbed. 15 and 20 are still absorbed. Doesn't look like this much here, but it took out WWV and WWVH, both of which are pretty strong stations. In this picture here, the black diamond in the middle is the position of the Earth when this screenshot was taken. And you can see that, maybe you can see that the absorption is very heavy right below the sun and decreases the further you get out. But over all of North and South America, absorption is really heavy from about 25 megahertz on down, as in fact we experienced. If you look closely here, you can see the edge of this disturbance heading towards Asia. And of course, as the Earth turned that way, the disturbance went towards Asia, and in the afternoon, Asia was heavily blocked out. This comment in the screenshot is interesting. The estimated recovery time from this solar flare is 1 hour and 17 minutes. Like heck it was. It lasted for hours, all day long. You can see here this screenshot was taken about 3 hours after we first saw it go up. And it's down to, well, a C class, which is still significant, and that's 3 hours later. So, that concludes the presentation. Communications is exciting and rewarding, and it's pretty important when you're in rural areas and mountainous areas, remote areas of the country. Just try having your RV break down in one of those places and discover that the problem is something you can't fix, and you discovered you have no cell phone connectivity. It gives you a bad feeling real quick. I can testify to that one. So it's important to know what the sun is doing and how that affects the ionosphere so that we can make good use of it. I was asked in the previous presentation to give some interesting URLs. Those are some of the ones that you got screenshots for. There's a partial list of references and a little bit of my background. Okay.